So again, that whole power thing, you know.
Yes.
No, I just need some,
I guess.
but it's about.
This must be a win.
Every.
I've been hearing reports of
So I didn't know if it was a little too much.
I just need to know if I need to remove it from my
It's
schedule or
about
not.
the way they drive.
It's like, I don't really care about what you're talking about for the next 50 minutes, Dr. Mike. I just need to know whether or not we're having homework.
No, my schedule's open. I'm about to close it.
Okay.
Is that-
So, no, we do not have homework today. So, yeah, the important stuff, right? So, just so everybody's aware, a little bit on the schedule. So this week is the week of welding. We're going to discuss welding Monday, Wednesday, and Friday. I'm considering making a very slight tweak to what we do in class on Friday because I would really like to cover balanced welding, and I think I can probably maneuver that in, especially given the fact that we were going to have a guest come in today, but they're not going to be able to make it. So I'm just going to make a post on Teams for the info that they were going to distribute. But let's talk about the schedule moving forward. So you're going to have a homework assigned Wednesday, due Friday, a homework assigned Friday, due Monday. The homework that's due Monday, why does that say due Wednesday? That is the typo. Sorry, I'm going to fix that now. This is Monday.
3.8.
All right. All right, so the homework that's due Monday, there are not going to be any late submissions because I'm going to turn the solution on Monday, right? So you're going to have the solution available the moment it's due. Monday of next week, we will do our exam review on bolted connections and welded connections. Wednesday, we celebrate. Friday, no class. Is that okay?
Very well.
Woo.
Woo! I'll wait.
I'm not going to lie, Dr. Mike. I've been waiting for your countdown of the class periods. I haven't heard yet how many we got left, how many we've had. That normally keeps me on track for the year.
Well, we're on lecture 21, so we're actually pretty much halfway there.
Look, see, that's all I needed.
That sounds so much better when you put it that way.
Almost.
Well, there's
Halfway.
41 lectures in the semester, and
So halfway through this class that we have.
halfway through the semester, right?
Yeah, that's great.
This guy said.
Yeah.
Yeah.
Okay.
Yeah.
We are halfway through the semester. Okay. We are going to begin our next module of the class discussing welded connections. I'll tell you that this is the shortest module in the class, and it's I would argue probably the easiest from a math perspective. Today, though, I want to kind of handle welded connections the way that I did bolts. If you recall, with bolted connections, we had one day where we kind of just laid stuff out, and then we got into the math, and I found that with welded connections, the same thing works as well. I didn't get the chance to grab any weld electrodes or weld sticks to pass around class. I'll do that on Wednesday. But I want to talk about welded connections first from a fabrication standpoint. I'm curious, how many of you have ever welded anything? Okay, all right.
Soldering.
No, soldering does not count. No. Get out. I'm just kidding. I'm kidding. I'm just kidding. I'll say this. I think I am a marginal to okay welder at best. But anybody who has ever welded anything will tell you that that welding is an art. Like it takes skill. It takes training. I mean, in regard to connections, I mean, to be honest, if you all were on a construction site and I wanted to train you on how to properly install bolted connections, we could do that in about an hour between the tools, the safety, all that. That's that. Welding's different. Welding requires years of practice, of training, of certification. It's one of the reasons why welders tend to make a fair amount of money. What I want to do is I want to talk about introducing you to welding from a fabrication standpoint, and then we'll get into the design. I'm going to talk about the 4 main types of welding methods that are used in structural applications. So I'm using some particular terms like shielded metal arc welding, gas metal arc welding, flux cord arc welding. I'm guessing that those of you that have welded before have never heard these terms, but you have heard things like stick welding, MIG welding, things like that. And so these are just the more proper scientific names for those methods. And they have applications where they're relevant and where they're not. One thing I will tell you is that one method that I'm not going to discuss is TIG welding. How many of you have ever TIG welded? TIG welding, I think, is where the real artwork is. I mean, I have seen some beautiful TIG welding before, but TIG welding is really not appropriate for large-scale structural applications. Most TIG welding is really done on mechanical applications where the welding needs to be very, very precise. And I'm not saying that we don't need precision and standards with structural applications, but it's not the same world. We're not really thinking in that scale. But don't worry, I've got a slide for each of these. So the first one I want to talk about is shielded metal arc welding. You probably know about that as stick welding, and I would say that stick welding is probably the most common type of welding that you see used in everyday structural applications. So first off, just to make sure that we're all on the same page, if you have never welded before, the first thing I want to make sure that is crystal clear is that we are not gluing piece of steel A to piece of steel B. That's not what's happening. In weld land, what we're doing is we are essentially completing a circuit between our essentially our weld machine, our field piece, and the weld electrode, which is essentially a consumable. Once that circuit is complete, we are essentially creating, all that, electricity flows, and we are essentially creating a molten pool of essentially three metals, both the workpiece, the element that I'm welding to the workpiece, and then the weld metal itself. Once that metal cools, we now have a welded joint. So welding requires a lot of energy input in order to make that happen. There is a whole field of science on the metallurgy and the chemistry required in order to properly deposit welds and to make this happen. So again, I wish I had brought some weld electrode with me to class. I'll bring that on Wednesday. Can anybody tell me what, if you've ever done stick welding, what the stick weld looks like? Like, there's a wire, but there's something else going on with the stick. Everybody? Yes?
There's like I guess it's like the flux around it. It's basically like a sparkler.
Yeah, there's a granular flux that coats the electrode. It sort of does look like a sparkler. It's kind of like this crusted sand looking stuff around the electrode. And that has a very particular purpose, okay? Once you complete the circuit, okay, and you start, energy starts flowing in order to melt the steel and the weld consumable, you are also activating this flux. And what happens is, right there at the point where the weld electrode comes into contact with the workpiece, that flux activates as well, and you are essentially generating a gas right there near the joint that is there to protect the weld from impurities in the atmosphere getting into the weld. One of the biggest things that we're really worried about getting into welds is things like excess hydrogen. Like if you get hydrogen in a weld, you can get hydrogen embrittlement, and brittle welds are really bad. Brittle welds fail very suddenly. They are brittle, they crack, we don't like that. So that gas essentially is there to prevent that from happening. That's what a stick weld essentially is trying to do. So whenever you're creating a welded joint, not only do you need to have the energy and the weld consumables necessary to properly affix the two pieces together in a cohesive joint, but you also need to deposit it in such a fashion that the chemistry is well maintained. And so in stick welding, that's what the flux is for. The flux is there to protect the weld deposit from any impurities in the atmosphere. Whereas in MIG welding, we do that a little bit differently. Instead of a flux that coats the electrode, in most MIG welding applications, not only do you have the weld that's on a continuous feed, but you usually have a a gas shield tank that's connected to that. Once you hit the trigger, not only are you depositing the weld electrode, but you're also depositing that gas as well. How many of you have ever done MIG welding before? What do you think is easier, stick or MIG? I'm just curious.
I like MIG because that's what I have, and then you can actually like weld more continuously. You know, your stick.
It's faster, yeah. You have a continuous feed of electrode in the machine. It comes on a drum, about like that big around, and it's continuous fed. The electrode to me kind of looks like copper wire. You know, it's a little different than that, but it's kind of like copper wire. Its funny thing is that if you, I have asked a lot of professional welders this question. A lot of times they think stick welding is easier. To me, I never really got that because, you know, if you're MIG welding, you just have to do this, right? But if you're doing stick welding, you have to maintain your horizontal movement and your depth as well. I always thought MIG welding was easier. That's just me. These are the two predominant means of welding used in most structural applications. There are some slight variations to that. One of them is what's called flux cord arc welding. So basically, flux cord arc welding is a lot like MIG welding, but instead of using a gaseous shield to protect the weld from impurities in the atmosphere, the electrode itself has a flux coating that protects it as well. You can usually tell flux cord welding when you deposit it because it has this sort of like white sooty like deposit after the weld. Flux cord arc welding, again, it's a lot like MIG welding, but it just, you don't need the tank of shield. Flux cord has a really cool application if you're ever welding in the field, right? If you're welding in the shop and you're using a standard MIG welder, you're not really so much worried about wind blowing the gas shield away, but you are if you're in the middle of the field, right? So if you're welding in the field, you probably want to go with a flux cord process because you don't have to worry about the wind blowing away your gas shield. So that's kind of a good benefit of that. Yes, sir?
I use the flux cord just because it's cheaper though, but there's a lot of guys online that will use the flux cord with the gas on top of it.
Well, they must be really worried about hydrogen environment, yeah.
Well, I guess it works out to make a really nice weld. Now I don't know about like the structural stuff if it's really that necessary, but it's just, I guess.
Well, one of the things I've found with stick welding versus MIG welding is you don't get the amount of weld penetration with MIG that you do with stick, and so with structural applications, you kind of need sometimes some pretty beefy welds. So now these are I would say the three most common weld applications that you will find done by human beings. The fourth is using robots. Okay. Now, I would say that arguably the most common new method to add to this list is what's called submerged arc welding. Submerged arc welding. So first off, this is only done by automated methods. This is the only. This would be a robotic application. Now, the big thing about SAW welding or submerged arc welding is that. Submerged arc welding is really, really good if you have a long, continuous weld that you're wanting to deposit. Like stick welding, MIG welding, flux cord arc welding, etc. I mean, those are really good to be done by human beings, and so you can do those for really long welds or really short ones. But submerged arc welding is really only good for long welds. A good example would be if you are fabricating a plate girder, and so you have a flange on top of a web, okay, and you want to weld those together. That is a single weld that is going along the entire length of the girder. That's a long weld. And so for the purposes of ensuring proper quality assurance and quality control and things like that, it's a good idea to let a robot do that type of weld and instead let the human beings handle the more intricate, complicated welds that require, you know, that degree of control. So the way the process works is that in order to protect the weld from impurities in the atmosphere, the weld is actually performed submerged, right? So the first thing that you will see is this deposit of granular material, and then the weld is done under that, and then the weld, or then the robot scoops that weld material up and keeps going. So the weld is actually performed underneath this granulated flux, hence why it's called a submerged process. It does allow for deeper weld penetration, but you really can only use that in flat weld positions or horizontal weld positions. We're going to talk about weld positions here in a second. Before we get into weld positions, I want to talk about the types of welds that we deposit. And don't worry, I've got some pictures of this so that you all can see this. I would say that first off, vast majority, the most common weld that you see in just about every single weld application is a tack weld, right? Everybody know what a tack weld is? What is a tack weld?
You just kind of stick something together real quick.
To make sure that it's lined up before you really put the weld. Because once you really put the weld down and you realize you screwed up, it's going to take a lot of grinding and a lot of work to get that piece separated. So a tack weld is a temporary weld to hold parts in place while more extensive final welds are made. So tack welds really are more of a concern from a fabrication perspective. They're more often than not something, you're not designing tack welds. That's just a fabrication concern, but I think you kind of need to know what they are. Now, as structural engineers, 90% of the welds that we design, specify, are fillet welds. Okay? A fillet weld is a bead of weld that is placed along adjacent members. And don't worry, I've got pictures of all of this. Beyond fillet welds, the second most common weld that we see is a groove weld. Now, a lot of times you won't hear them referred to as groove welds. You'll hear them referred to as things like complete joint penetration or partial joint penetration. Sometimes they're called PJP or CJP welds. Essentially, those are made to splice two plates together. They're not really very demanding from a design standpoint because you're speccing out the weld to develop the full capacity of the plate. You just need to be aware of them. Every now and then you'll see plug and slot welds, but they're not all that common. Okay, here's some pictures. I think pictures are great. So these are tack welds. So again, tack welds are just a second or two hit of the trigger on the MIG weld, or a second or two hit of contact with the stick, just to get the pieces attached to one another, just to make sure that everything's square and measured up and lined up correctly before you actually deposit the weld. The most common structural weld that we design as civil engineers is a fillet weld. So a fillet weld, again, is a bead of weld that we place along two pieces in order to attach them together. So you will see connection plates attached to columns using fillet welds. You'll see extended end plates for beams. I mean, this is the vast majority of what we do as structural engineers is done using fillet welds. Groove welds, again, a groove weld is really where you're trying to splice plates together. You're literally trying to take plate A, plate B, splice them together. And so what you're doing is essentially cutting a groove in the plates and filling them with weld metal. That's why the class of them is groove welds, but the most common ones that we see in applications are complete joint penetration or partial joint penetration. Plug welds, not very common, but you do see them every now and then. That's where you have a hole drilled in this plate, this upper plate, you lap it on top of the lower plate and fill that hole with weld metal. Uncommon, but common enough that they're in the specification. So, okay, here are some of the terminology that you will see for welded joints. So what I mean by welded joints are when you're taking plate A and plate B and slapping them together. How can you do that? We've already heard the term lap joint. We've already talked about that with bolted connections, so a plate lapped on top of another and a bolt through them. Now we're going to be looking at depositing fillet weld along this area here to fuse the two plates together. T-joints are also incredibly common for things like flange to web connections. And then butt joints, these are pretty common for two plates butted up together. These are pretty common for groove joint or groove weld applications. All right, this right here is probably much more salient or important to those of you that have done welding before, okay? If you've ever welded before, you will know that it is easier to do this than it is to do this. Am I right? that the most difficult weld to deposit would be an overhead weld, whereas the easiest weld to produce would be a flat weld, right? So the way I have this lined up is this is sort of an increasing level of difficulty. So I would say that flat welds, like maybe this T-joint right here, this lap joint, are among the easiest to deposit, whereas overhead welds are among the most difficult to deposit. Anybody ever done an overhead weld before? I'm just curious. They're hard. They're also kind of a little dangerous, because you're like, hey, here's this molten metal, you know, please don't fall on me, you know. Anybody done any vertical welds before? I've done some vertical welds before. They're kind of hard. I welded, when I was in the structures lab, I had to weld some connection plates to the end of a beam, and so I'm welding it like this. It was kind of hard to get a nice bead on that. That was about the limit on my the test of my difficulty. Flat welds and horizontal welds, not too bad, but they start getting a little bit more difficult when you go past that. I think the main point that I want to get across to you as engineers is, you know, it is our responsibility not just to do the math and make sure the connection has adequate capacity, but I want you to think past just solving the equations and getting an efficiency of 90% or better. I want you to ask, are you speccing out a structure that is going to be easy to fabricate, right? Are you proposing a connection arrangement that is going to require an overhead weld in the field? Right? Why? Is there a better way of doing it so that you don't have to worry about doing that? That's an expensive weld to produce, it is a difficult weld to produce, and it is a difficult weld to produce in adherence with specifications. So try and avoid it if you can. You kind of need to be thinking about that on larger design projects. Okay, have you ever seen weld drawings? They can be a little mess, okay? They really can be kind of complicated, especially if you start looking at weld drawings on mechanical applications, because the symbology and the legend that we use to explain how welds work can get really complicated. Essentially, whenever you are defining a weld, there is a standard series of symbols that we use, and they all have a certain meaning. I'm not going to expect you all to do all of this. This is way more complicated than what we need to do for the purposes of this class. However, there are some that I do want you to be able to spec out, okay? And the ones that I'm interested in you being able to understand are these right here, okay? So I have here two weld schematics, and I want you to be able to understand these weld schematics and these pre-qualified joint symbols for the purposes of this class, okay? So what I have here are two plates. These are two T-joints, okay? And I have a weld specification. So the one here on the left, I have an arrow pointing here, and I have this 1/4, this triangle looking thing, and this 6. Okay, so what does this mean? Okay, so first off, the triangle corresponds to the fact that we are depositing a fillet weld. Okay, if you look here on the previous slide, we've got a triangle means a fillet weld, this means a plug or slot weld, you know, this means a back weld, etc. So whenever you see this triangle, that should correspond to fillet welds. As I said, the vast majority of welds that we spec out as structural engineers are fillet welds. So I want you to recognize that triangular symbol, because it is something that you very much will see on drawings that you are responsible for as structural engineers. Okay? Now, the difference between this symbol over here on the left and this one over here on the right, so you look here on the one on the right, we only have one weld that we're speccing out, versus the one on the right, we have two, okay? So notice here how the triangle is on the side of the text. What that means is that the weld is on the side of the arrow, okay? Whereas over here, I have a triangle on both sides. That means that I've got the weld on both sides. So if I wanted the weld on both sides, I would just put both triangles. Does that make sense? Okay, now the 1/4 of an inch corresponds to this dimension right here, the width of this weld here, and the width of this weld here, same thing here and here. The number 8 and the number 6 correspond to how long the weld is. So this weld here would be a 1/4 inch fillet weld that's 6 inches long. So 6 inches long outside the screen. Same thing over here, this would be an 8-inch weld, 8 inches out of the screen, okay? Those are the welds that are the weld symbols that I want you to be able to understand. And don't worry, we're gonna have exposure to this here in the not too distant future, so don't worry, it really won't be like information overload today. Does that make sense? Okay. Any questions so far? Okay, now, let's talk about the math. Let's talk about the capacity according to AISC specifications. And so really what we've got to wrap our heads around is this concept called the effective throat of a weld. And then we'll look into the specifications. Okay. Now, I have here a schematic that kind of shows a fillet weld in a little bit more detail. So let's look over here on the bottom left. So what I have here is a plate, and now I have the weld deposited. Now I'm obviously idealizing the weld because I'm drawing it as this nice, pretty 45, 45, 90. We all know that welds aren't that perfect, but for the purposes of specification generation, this is good enough to at least kind of idealize the geometry. Now what I'm going to do is define the effective throat, which essentially is what defines the capacity of the weld, as the distance from the root of the weld to the face of the weld. So if I know the size of the weld, I can determine this distance with a little bit of trig. It's almost like this distance is related to, I don't know, like the sine of 45 degrees, or the cosine of 45 degrees. And I think that's about 1 over the square root of 2, or 0.707, right? So the idea is that if I know the size of the weld, I can compute the length of the effective throat as the size of the weld times about 0.707. Does that make sense? Everybody okay with that? Okay. See, when we define the capacity of fillet welds, we are essentially defining that capacity based on this effective throat distance. See, ultimately what we're going to have is a stress times an area. And the area is going to be defined as the length of the weld multiplied by the effective throat. So as long as we can compute the effective throat, we're good to go. Okay. Now, so how do we compute the capacity of a fillet weld? Well, if you remember with bolted connections, we have a bolt shear and a bolt bearing limit state. So we either ask ourselves, is the bolt going to fail or is the plate going to fail? We kind of say the same thing with a welded joint. Is the weld metal going to fail or is the base metal going to fail? So we have that the capacity is defined as the stress times the area, the stress times the area. The problem is that this is just the section of the code that defines the strength, but all of these terms about the area, the phi value, the stresses and all that are defined in table J25. Let's all turn to table J25. J25 is on page 16.1-124. This is kind of a big table. There's a lot going on this table. I believe actually what we're looking at starts on page 125. I think it's on the next page because table J25 is really kind of big, but it's really kind of an important table in the spec because what it does is it lists a lot of capacities of welds all in one table, whether it's a plug weld, a slot weld, a groove weld. It's all kind of in that one location in the spec. Okay. Now, I want to make sure everybody's here. All right, so I think you're on the next page. I think this is on 125, am I right? Okay. Now, if you look here on this top row, so as you go through table J25, there are these rows that'll say like groove welds, plug and slot welds. Here I'm on the section that defines the capacity for fillet welds, okay? And so if we look at fillet welds subjected to shear, which we're going to assume all fillet welds are subjected to shear, we have the base metal capacity and the weld metal capacity. Let's look at the weld metal, okay? So weld metal, what do we know? Well, we know the phi value is 0.75. Good to go there. What about the nominal stress? Okay, let's talk about that. Okay, so the nominal stress is defined as 0.60 times FEXX. I told y'all that 0.6 was going to keep showing up whenever there's an element related to shear, right? Where does that come from?
We're serving out of the name.
Oh my goodness. Comes from the von Mises yield criterion.
I don't know how someone would miss that on the exam.
You don't know how somebody would miss that on the exam?
Don't know.
You know, I'm tempted to put it on this exam too. I'm just kidding. Okay, so if we assume that welds resist load through shear, then the nominal stress is going to be some electrode strength multiplied by, that characteristic constant 0.6. Now, where do we get the electrode strength? We get the electrode strength from the product, right? So if you've ever gone to Home Depot or Airgas or a place like that and actually buy weld electrode, it comes in a little box and it'll say things like E60 electrode, E70 electrode. Those of you that have welded before, have you seen that before? See what I'm talking about? Well, this number here, so for example, this is a common weld electrode, so this is E60. E60 means that the electrode strength is 60 KSI. That's what that number means, right? So if you take that number, adjust it by 0.6 because it's being loaded in shear, not in tension, that's the maximum stress of the weld metal, okay? So there's the phi value, there's the point, the stress. What about the area? The area says see section J 2.2a. So I turn to section J 2.2a, and what does it say? It says the effective area of a fillet weld shall be the effective length multiplied by the effective throw. So phi is 0.75. This is my stress. This is my area. The area is the length of the weld times 0.707a. And by golly gosh gee, there's how we compute the strength of a connection according to its weld metal capacity. Pretty simple, pretty straightforward. Okay. So far, so good? Now, that's the weld metal capacity. What about the base metal capacity? The base metal, we have to turn to section J4. And I just want to take a step back and just say, look, unfortunately, with structural specifications, and this is true with just specifications in general, there's a tendency to hop around from section to section with the document. It's like you're looking here and it tells you to go here. You're looking here, it tells you to go there. That's just kind of how specifications work. Just kind of got to get used to that. And I'm not saying that's just a steel design issue. I think that's just an issue with engineering specifications in general. You are trying to solve this problem. So you're looking for a specification that will tell you how to solve this problem. But that's not how specifications are written. They're written to help engineers solve any problem. So to solve your problem, you might have to hop around a little bit. That's just kind of the name of the game, okay? Now, if we go to the capacity of the base metal, there are essentially two different limit states we have to ask: whether or not the material is going to yield under shear or whether or not it's going to fracture under shear. But fortunately, we're seeing a lot of terms that we've seen before. Things like the gross area in shear, things like the net area in shear. We've seen a lot of this before when we did block shear, right? What's cool about welds, particularly fillet welds, are those areas are a lot easier to compute. We are not dealing with bolt holes. Like, what is the net area? The net area is the gross area minus the area lost due to the presence of bolts. We're not talking about bolts, we're talking about welds. So in general, for fillet welds, the gross area and the net area are the same. We're not removing any material from the connection in order to generate a fillet weld. That make sense? Now, the one thing you do have to pay attention to is that for shear yielding, the phi value is 1. For shear rupture, the phi value is 0.75. So, whoops, sorry. So this is kind of what we get. We get our welded connection summary capacity. Here's our weld metal capacity. Here's our base metal capacity. Oh, we're doing great on time. I might pull up our next lecture to pull up some things real quick, just to get us moving forward on our next example on Wednesday. Does everybody have this? Yes.
The 0.707, where exactly did those numbers come from?
So 0.707 comes from trig, right? If you have a it comes from this. So if you specify a weld size, right? So look up here. If you specify a weld size, how do you get this distance? I'm saying this is a 45, 45, 90 triangle, right? And I'm saying if you know this distance, then that's just a sine or cosine of 45 degrees. What is the sine of 45 degrees?
0.707.
That's all that is. It's just trig. So does that make sense?
Yeah, because the 119 page, he said defective barrier.
And that's
I
what
just wondered how you derived the equation.
it's not coming. That part isn't coming from the spec, but it's just coming from the trig. So that makes sense. Now, the only other thing that we haven't discussed, which will become important when we do our example on Wednesday, but I kind of want to just mention it now, is some limitations on welds. Okay. I'll talk about the weld orientation later. Okay. Like with bolts, if you remember with bolts, there was an analogy about whether or not bolts could be spaced too close together or bolts could be spaced too far apart. And there were reasons why we had limits on spacing, right? Now, for bolts, it was if the bolts get too close together, we can't get a wrench around them. And if they get too far apart, we'll get water seeping in between, okay? Just as there were limits for bolts, there are limits for welds, but the limits are for different reasons, okay? Now, I propose that for fillet welds, there are limits on the minimum size of a fillet weld, and there are limits on the maximum size of a fillet weld. So table J2.4 will tell you what the minimum size of a fillet weld is, but the minimum size is for a different reason. Okay, and I want everybody to sort of imagine a very cartoonish scenario, but I think the point will be gotten across. Imagine if I was welding two plates together, and those plates were 4 inches thick. Huge, right? Right? We're talking about steel that's like that thick. And imagine I deposit a weld that's only a 1/4 inch big. That's a super tiny weld, right? Now let's go back to how a weld is deposited, right? You're completing a circuit, right? So once that electrode comes into contact, the electricity's flowing and you're depositing energy, right? But if I have this 4 inch thick plate and only a 1/4 inch weld, what I'm proposing is that that super thick plate is sort of acting like a heat sink, right? It's absorbing all of that energy, and so the weld you deposit won't behave the way that you want it to because all that energy that you deposit for that tiny weld got absorbed by the plate. In other words, you get a heat sink effect, okay? I propose that if you're going to deposit a fillet weld, that fillet weld needs to have some size to it so that you don't get rapid cooling of your weld and loss of weld ductility, okay? So dependent upon the material thickness of the parts that you're joining together, you have some minimum size of a fillet weld to try and avoid that heat sink effect. Does that make sense? That is the reason for a minimum fillet weld size. The reason for a maximum fillet weld size is so that you don't melt the plate, okay? So imagine if you're trying to weld two 1/2 inch thick plates together. You kind of have to back off the weld a little bit because if your weld gets big enough to be the thickness of the plate, you will start melting the plate and then you won't have proper weld geometry there where the plate and the weld meet. Does that make sense? So for most structural connections, what we're having to do is if we want to determine the maximum weld size, we take the thickness of the plate and we back it off a 1/16 of an inch and we say that's about the maximum size that your fillet weld could be. for most connections. If you've got a really thin plate, like if your plate is a 1/4 inch or thinner than a 1/4 of an inch, so we're talking about, you know, really thin plates, we say, what the heck, just, you know, fill the whole thing up, you know. But if you have, for most structural connections, we got to back that off a little bit so that we maintain the geometry of the plate. So yeah, so for minimum weld sizes, we're trying to avoid the heat sink effect. For maximum weld sizes, we're trying to avoid distorting the plate by melting that corner up there. That make sense? All right, any questions so far? All right, I have, I think I've probably reached my desired, I don't really want to information overload you today on welds. So we're going to get into this example on Wednesday where we look at the capacity of a fillet welded connection. But I'm gonna leave that for Wednesday. Today, I kind of want you to absorb this info. What we'll do is we'll come back on Wednesday. We'll go back, review our weld capacities, go back, talk a little bit more about ductility and what have you, and then we'll get into some of the math. I think you're going to find that when we actually start digging into the mathematics, this is pretty easy. But I want to kind of jump ahead a little bit because I want to make room for balanced welds a little later. I'm going to pull up the code one more time in case you didn't get the code, but that's all I've got. I will see you all next.